Hello everybody. Our next lecture is about mechanical testing of composites. In our previous lecture we discussed about how we can test composite materials or anisotropic materials in general. Here we will narrow our focus. We will look at only composite materials and we'll look at 4 specific type of tests and how you can test them. The 4 different type of tests are tension, flexural, compression and shear. These are by far the 4 most common tests that you will have to do. Before we proceed further, I want to remind you that just like yesterday, I will also be sending another Google form today. So any doubts, questions, you are free to ask. I promise to compile them and send all the answers in depth as much as possible. So without further ado, let us now understand how we can do tension tests. So in tension test, basically you are looking at a sample and you try to apply load and you try to pull it apart applying loads like this. The idea is that you keep on applying load in a quasi-static manner till it breaks into 2 pieces. And there are few requirements that you should keep in mind. First, the specimen should be long and slender. Why? I will come back to that in a few minutes. You have to put end tabs to reduce failure in the grips. For example, if I apply a load as shown by the arrows, my sample should not fail here. If that happens, it probably means that my testing method was faulty. So, and then the next question which you logically ask is, what should be the gauge length? What should be this L? What should be the length of the end tabs? All this will depend on the standard that you use. If you remember yesterday in my previous lecture, I have said that there are a large number of standards, and before doing a test, you must finalize the test standard, and the test standard will depend on which sector you are working for, which country you are working for, whether there are legal implications of the test, so on and so forth. So depending on the testing standard for composite materials, I am listing here 3 test standards: CRAG, ICI, ASTM and a specific ASTM standard for tensile testing of composite materials. And the total length depending on the standard has to be 200, 283 or 228.6. Keep in mind that I have not put the units in this table because these are in the same units as the thickness. So if thickness is 1, then the total length has to be 200. If you open an ASTM standard like, let's say, for example, this one, then you will see that the length that is provided varies from, they'll say something like put it between 1 to 2 millimeters or 1 to 3 millimeters. And depending on what thickness that you use, the length, gauge length and the width will accordingly vary. So even though I'm putting here fixed numbers in this slide, the testing standards do not require you to put fixed numbers as such. There is always some range for leeway. It is not like you have to have thickness of 1 millimeter, and for some reason if you have a layup sequence where the thickness is 1.1 millimeters, doesn't mean that you can no longer use this test standard. There are usually limits. And another point worth noting is that as an institute we have access to our ASTM standards. So apart from this, watching this video, one important activity which I highly recommend all of you to do is to read the ASTM standard D303976, which I will share by email, so that just to have a feel that how standards are written, what are the things that are mentioned, etc, etc. I can give you as much lecture as I want, or you could hear to as many lectures as you want, but you will not get the real feel unless and until you do the tests. And since the current situations, maybe we will not get to do the test, the next best thing is to at least read the test sample. There very detailed and precise instructions are given on how to prepare the sample, how to cut it, what should be the length range, what should be the gauge length range, so on and so forth. Now it also depends on the orientation of the sample. So as you know from your class that a 0 degree sample can be expected to have high modulus, high strength. The 90 degree sample not so much. and there are different modes of failure for 0-degree samples or 90-degree samples. Accordingly, the ASTM standard prescribes different length. Again, these numbers that you see are based on the assumption that thickness is 1. If thickness is 2, then you multiply everything by a factor of 2. And also, if you look at this slide, you will see that the prescribed width for 90-degree samples is twice as much as 0-degree. Can you guess why? Think about it. I will tell you the answer in the next lecture. So now, when you apply a tensile load, there is a possibility that your material could fail in this region where you have actually put the clamp. So actually your machine is holding the sample like this and you are applying a load. Clearly you are only interested in what happens in this region. If it fails anywhere other than this region, then means your testing is faulty. So to avoid failure in this region, we will put what are known as end tabs. So if you see at the two tips, the width is slightly bigger. These are known as end tabs. Now you can put two types of end tabs. One would be a regular extreme tapering end tab that I have shown in this figure. The other could be a regular end tab where there is no incline like this. Rather, your end tab ends sharply in this region. So, and it is shown that depending on how you taper it, there will be slightly different properties of strength. So there have been reports where people did a large number of tests for carbon fiber epoxy UD composites with extreme tapering as shown in the figure and also with regular end tabs. And extreme tapering shows that the strength of the composite is about 300 megapascal higher and the variation is also low. So again, this brings me to the end, the previous lecture where I said that the testing standard should be equal to your material. Your test should be equal to material property. Then the question is, which is the material property? Is the strength 2410 or is it 2120? The answer is it is likely to be 2410, not 2120, because in extreme tapering we are reducing the stress concentration. So the lower value that you are seeing for your regular end tabs is most likely due to the fact that there are some stress concentrations due to sudden change from tab region to no tab region, and that is causing all the problem of reduced stress, more variation, both of which is undesirable. Now when you do the test, you can expect to get a stress strain curve like this. And what are the different tests, what are the different properties that you can extract out of this? Remember, in our previous lecture we said that if I do a sample test, then the data acquisition decision has to be made. I can extract from some tests I can extract large number of data, from some I cannot. For example, when I do a structure testing, the data was okay or not okay decision, but when I do a material level test, then I can take out maybe larger number of data. For example, if you do a tensile test, you get a curve like this. You could calculate the Young's modulus, which is the slope of your material at the initial stage. You could calculate the strain to failure, you could calculate the stress to failure. You could also calculate the toughness, which is the area below this curve. Area below this curve is an indicator of the toughness of the material. So there are at least 4 or 5 different properties which you can calculate. If you have more than one strain gauge, or if you're using digital image correlation, you can also calculate the Poisson's ratio. Basically, you need to somehow measure the deformation in the other direction. If loading is in one, you need deformation in the two direction, and you should be able to know also the Poisson's ratio. So one test, multiple results. The next type of testing is what is known as flexural testing. What is flexural testing? Is how my material behaves when subjected to bending loads. So flexural testing is done usually to determine the response to bending loads, and you usually have what is known as a 3-point or a 4-point bending. In the figure you are seeing, this is a 3-point bending test where you have a rectangular sample, it is resting on two rollers and you apply load at one point. Now instead of one roller you could have two rollers, maybe one here where you apply load. That would be 4-point bending. Now this is very relevant for a large number of composite applications. In fact, there is a family of composite material which is designed specifically to take bending loads. For example, in our last theory class in classroom, we learned about sandwich materials. These sandwich materials are exclusively used when there is bending material, when my material is expected to be subjected to bending loads. So flexural testing is very, very important. Now what are the differences with tensile loading, or tensile testing? So flexural loading versus tensile loading, under normal test, the flexural loading sample is usually simple. It's a normal rectangular sample. There has to be no end tabs, because if you look in the figure, in the picture that I've shown, it's a normal rectangular. It is resting on two rollers. This is two support. This is support number 1. This is support number 2. And the load is applied at 2 points. So this is an example of a 4-point bending test. If you look at the sample, there is no end tab. We don't need an end tabs for this type of loading. And if you also look, the displacements are much larger, so much so that you can actually see. Most likely it was a straight line like this when it started, and after applying you have this displacement, which is easy to see. So there are larger displacements which are easier to measure. You don't need sophisticated equipments like digital image correlation or strain gauges. A simple deflectometer as shown in the figure is enough to measure the displacement. And other big difference is that the outer and the outermost layers will subject more to strength and stiffness. When you are doing tension test, throughout the thickness, the contribution to modulus is same. The contribution to strength, if it is all the fibers have the same orientation, is same. For bending, that is not the case. The other change is that when I am applying tensile load, every layer is subjected to tension load. But when I am applying bending load, I can have compressive stress at one outer surface, tension at the other surface. So it means that my material could actually fail due to compression or due to tension. So the mode of failure is sometimes not known a priori. So what are the normal standards for ASTM or any other test standard for bending type load? For 3-point bending, usually the length is in the order of 90 to 140 times the thickness. The span also varies. There are some, but mostly the length should be equal to the span, and the width is about 10 times the thickness. Span here means the difference between the two supports. Length is the length. So this is your length and this is your span. Okay, this is your thickness, and the width would be seen if you would look at this image from above. This is the side view. Test description. So when you perform the tests, your sample is resting on two supports. You apply a load force which is directly measured from the load cell, and the central displacement, it could be measured by using either the crosshead displacement or you put some sort of a extensometer, LVDT, which is just below the central loading point. So you have some sort of deflectometer here. You measure the distance. Keep in mind that the shear loads are usually present, but you are neglecting it. And then depending on your dimensions of the specimen, if you know delta and if you know the load P that you have applied, you can calculate the maximum stress. We have learned about this briefly in our theory class. And once you know the modulus, you can also calculate the effective modulus using a formula something like this. This is true if 60 h square by L square is much greater than 1. In that case, you can neglect shear. So let us now look at typical answers of typical effective modulus of, let's say, cross-ply symmetric intermediate modulus carbon fiber and epoxy 090 symmetric. So it's 090 90 0. And if you do a tensile test either in the x direction or y direction, it's going to be approximately equal to 108 gigapascal plus minus some standard deviation. However, the flexural E modulus in the x direction and in the y direction is going to be much different. First of all, the flexural modulus is higher than the tensile modulus in the x direction and significantly lower in the y direction. Can you guess why? Hint is, think about the D matrix. So this is symmetric, B matrix is 0, D matrix. It depends on the ply layup sequence. When I am looking at bending in the x direction, my ply sequence is 0, 90, 90, 0. So the 0 degree plies which have high modulus are on the outside. So they can take a lot more bending load. But when I am rotating my sample by 90 degrees, now it becomes 90, 0, 0, 90. So my 90 degree plies, which are generally weaker and contribute less to stiffness and strength, are on the outside. Therefore, a 090 cross ply will have different stiffness in the x and y direction but same tension properties in the x and y direction. This is coming directly from your classical lamination theory. And also important point is, even though absolute numbers are written here, a correct thing to do would have been to say plus minus some value. And you will notice that, and I will come back to this later, you will see that this scatter for bending is much higher than the scatter for tension. So x will be much higher than y. And why is this so? We will discuss in a few minutes. Now let's say you took a sandwich panel, you tested it like a 3-point bending, schematic representation shown in the figure. It can fail due to many ways. Okay, you can have the top or the bottom layer is failing due to tension, the top layer is wrinkling due to compression, something like this. It could be shear failure of the core, and it could also be that some layers just delaminate. Now the question to you is, which of the following do you think can be modeled using classical lamination theory? The answer is the deformation and fracture of the skin can be modeled. This is basically tension in the outermost layer, which we can calculate. Skin wrinkling is compression in the outermost layer, which we can model. Shear failure of the core is through the thickness shear, which we cannot model. Kirchhoff-Love assumption is based on the idea that each of my layers is in a state of plane stress. Delamination is usually a defect based damage, which we cannot model using our classical lamination theory. So if I do these tests and I find out that my failure was due to this mode or failure was due to this mode, then the strength prediction from my test is not accurate, because the expressions for maximum stress have been derived assumed by neglecting shear. So a few minutes ago I discussed about how there is a large scatter in 3-point bending test, and it is usually higher as compared to tension testing. Can you guess why? If you have paid attention to my previous lecture, maybe you will be able to guess. So we talked yesterday that for a brittle material you can use a Weibull analysis, and this V is your volume of the gauge length. So for a tensile test the gauge length is usually of the order of 1600 or 1600 into 8 millimeter cube, depending on how thick samples have you used. But if you have a 3-point bending test, the load is applied at a very narrow thin region, and the volume of that thin region will be somewhere equal to 0.05 into h into 0.1 L into the width. So the load is applied. So if you see the load, it is applied like this, and you apply a load like this, correct? So load is applied over the entire width, but it's in a very small part of the entire gauge length, and usually the volume where failure is likely to happen, where there is stress concentration, comes out to be only 2.5 millimeter cube. So the volume is very low, and hence if I put everything else remains the same, if the volume is this much different, you can see that the scatter difference will also be very high. So how do you escape scatter? One strategy is to, let's say, instead of a 3-point bending, use a 4-point bending. When I am doing a 3-point bending, my load, the area of interest for strength is just this volume, the volume of this cross section, which I have calculated to be about 2.5 in my previous slide. So it is this region. Now if I apply a 4-point bending test, where instead of P at a point, I am applying P by 2 at 2 points, the region where my material is getting highly stressed is this. So the volume is increasing significantly, and if I put it in my Weibull distribution, as the V increases, the scatter reduces. So for a composite material or a heterogeneous material, sometimes it might be a good idea to use a 4-point bending test as compared to 3-point bending test. This will significantly reduce the scatter. But then you need a load cell with much higher load capacity. For example, for a 3-point bending test, this maximum moment is twice the value of this, because I have applied P by 2. So my load cell capacity has to be a factor of 2, which is usually not a problem for these type of materials. We do have load cells at that capacity, but the scatter is significantly lower for 4-point bending test as compared to 3-point bending test. Another way of understanding this phenomena is to suppose, let us say, you don't like statistics, you don't want to understand this on the basis of Weibull, but you want to understand in basis of more physics and intuition. Then consider the following. Let's say you have a composite material, and somewhere there is fiber, somewhere there is matrix, and depending on sample to sample basis, exactly the point where you apply the load, you can have a fiber, you can have a matrix, or you could have a region which has 50% fiber, 50% matrix. So depending on where you are hitting the load, matrix, fiber, or fiber plus matrix, you can get different type of loading, different type of strength. Now in this case, I can have fiber and matrix, but since I am applying uniform load over a large amount of area, there is some sort of averaging. So the stress concentration is not at an unknown point where I don't know there is fiber or matrix, but stress is now at a well-defined region where I have both fiber and matrix. So the scatter is much lower. So tension is done, flexural is done. Now let us look at compression. Compression testing is basically you take a sample and you want to find out what is the strength if you apply compression, as opposed to this is tension and your compression would be you try to press it. Now compression testing is usually tougher. Compression testing is usually tougher than tensile testing. Why? First is you want to avoid buckling, and if you want to avoid buckling, you need a slender specimen. This results in geometry dependent lab tests. For example, if a person A does a test where he doesn't have a slender specimen and person B does a test where there is a slender specimen, results will be vastly different. On the other hand, if all of us use slender test specimens, the test setup is significantly tougher. I can get more scatter, I have to avoid scatter, I have to avoid buckling. So compression testing is usually tougher. And if there are situations where I can assume that the tension modulus is the same as compression modulus, or the tensile strength is the same as compression modulus, there is always a temptation to do that. So what are the things that we have to avoid? Buckling, obviously. You have to avoid axial misalignment, meaning if I want to find out the compression strength of 0 degree UD fiber, even slight misalignment of 2 to 4 degrees will cause a large error in the strength, as opposed to tensile where this is not so serious. And you also want to avoid splitting at the ends. And broadly there are 3 types of tests that you can do. One is a type 1 test where you have short gauge length, type 2 where you have gauge length which are of acceptable length but you support them laterally, and the other miscellaneous we put it into one category. So the reason for mentioning that there are 3 types of tests is that unlike tensile test where more or less universally it is agreed that I must build a thin long sample, I must put tab lengths, I must apply load, the test setup for compression is not universal. Different test standards will suggest different things for you, and depending on the test the values will also be slightly different. So that's why this is also one reason why you have company based test standards. So assume that there is a company which has done all its compression tests using type 1 tests. So if not anything, you can calculate and you can compare 2 materials if all have been done by type 1. Let's say it has done all its tests by type 1, you have done it using some type of type 2 test, then it's not a one-to-one comparison of the strength. It is very difficult to say which material is better. Therefore, this is also one reason why we have test standards. So the first type of type 1 test is what is known as IITRI test, where basically this is your sample, this is your gauge length which is very small, and you apply compression load from this. Now advantage of this is that you have a slender specimen which is not going to buckle. Disadvantage is the entire fixture is quite heavy, and in this narrow region where you are interested you can have a non-homogeneous stress field where maybe in this region you have high stress, maybe here you have low stress, etc., which you should avoid. So this does not give you a very accurate or repetitive idea about the strength, but it is useful for comparing. If you test 2 materials by exactly the same test standards, then you can say material A has higher or lower compressive strength or modulus as compared to material B. The second type 1 test is what is known as the Celanese compression test, where this is the sample, it goes somewhere here and you hold it by these 2 samples and then you apply the load. Once again, slender specimen, buckling is prevented, all good, but problems are you are introducing friction because the outside surface of this interacts with the inner surface of this, causing some sort of friction which you don't like. Non-homogeneous stress field like the previous case, and this test setup is very complicated and expensive. Sometimes this test setup can be more expensive than your UTM itself. Type 2 test, where you apply some sort of support. So instead of using this is my test specimen, instead of using a slender specimen, I apply supports at 2 edges. So we apply a load like this. If this is starting to buckle, the supports at the 2 faces will not allow it to buckle. Good thing is homogeneous stress field is there, buckling is prevented, but as soon as there is onset of buckling which these face supports will stop, there is a change in the stress field. So again, the strength values are not expected to be very reliable by this method. Our last topic for today is how to do shear testing. Shear testing is very difficult because no matter how you apply a pure shear load, there is going to be some anisotropy. There is going to be some non-homogeneous stress field due to anisotropy. And even if sometimes there is shear stress but there is also some small component of normal stress, it will lead to tensile failure. But you want a shear failure because you want the shear stress. That is usually not possible. And then also there is a question of how to get plane stress or how to get interlaminar shear stress only. I want a state of stress where I only have one component of stress, one component of in-plane shear stress, which is sometimes difficult. There are large number of tests. Each of them have its own advantage and disadvantage. Quickly let us look at each one of them. The first one is, which all of you are familiar with, is the torsion test. You take a circular sample, you apply a torsion load. Advantage is that it is simple, it is well known. You have pure shear in the central area. If shear wall thickness is small, it is more or less homogeneous. But the problem is alignment. Sometimes some degree of misalignment can give you wildly varying results, and introducing the load is sometimes difficult. So if I have a thin walled circular specimen, this is a good test, otherwise not. The other method is what is known as the rail shears test, where this dotted line, this dashed material is my specimen. It is clamped at two places and load is applied through this. So basically you have a sample, you are holding it at two places, and at the third place you are applying load. So you can expect to get pure shear in this region, where if you put a strain gauge, you can calculate the modulus and the failure to stress. So the positive thing is there are regions of pure shear, which is nice. If I put the strain gauge, I can get the shear modulus accurately. So this is a good method to calculate the shear modulus. Not so much for shear strength, because there are holes here where you have stress concentrations. Depending on how the hole was made, who is performing the test, the reproducibility is difficult, where test results by one person can vary from test done by other person, or one lab can vary from other lab. This is a good method only if you are interested in the shear modulus only. The third is IOC-Pescu shear test, where basically you have a notch sample like this. You have two ends supported by rollers and you apply load. This region can be expected to be in a state of pure shear. You can calculate the strength and modulus quite accurately if you are able to avoid the stress concentrations here. If you are able to avoid the stress concentrations here, this is perhaps one of the better tests. But by far the easiest way to calculate the shear modulus is to take a plus minus 45 degree sample, perform a tensile test, which as you know is very simple, it is very standard, and then you can calculate the shear modulus using simple formulas like this, where the shear modulus is nothing but the applied load P divided by 2 into width into thickness, strain in the one direction minus strain in the two direction. So again we are finding the shear modulus, but we are doing uniaxial tension test in a plus minus 45 sample. This is a very good method if you are only interested in the shear modulus. This is more or less straightforward. You don't need any new type of test rig or equipment. But the problem is the final failure is going to be due to tensile stress and not due to shear stress. So the value that you get for shear strength by this test is not the shear strength, it is some other value. For only modulus, this is a very good test. The other possibility is to use a off-axis tension test and use some sort of asymmetric laminate and use 3 strain gauges. So let's say you use plus minus theta and you apply 3 strain gauges, apply a normal tension test, and then you can do some back calculations using what we have learned in the class about transformation of strains, and based on that you can calculate the shear modulus. Again, this is a good method if you are only interested in the shear modulus, not the shear strength, and you need 3 strain gauges because you will need the strains in 3 different directions. And disadvantage of this method obviously are 2. The first is that for different materials there are going to be different optimal angles. For carbon epoxy, it is known that if I want to use this method, I must use it at 10 degrees. For glass epoxy, maybe the number is slightly higher or lower, we don't know. And second is, you get strain data from the 3 strain gauges and then you have to do some calculations to calculate the shear modulus. This is doable, but some post-processing is needed. So this test cannot be achieved only by a lab technician. Let us calculate the interlaminar shears test. How do we do that? We can use what is known as the short beam shear test, where you have a very small sample you apply a 3-point bending test. Now if you recall, 3-point bending test is used to calculate the bending properties. But if my gauge length is very small, then you can calculate the bending moment, which comes out to be something like this. So the maximum bending load is a function of your gauge length, but the maximum shear strength is not a function of my length. So this maximum bending load can tend to 0 if my length is small, but my shear strength remains intact. So based on this, we can calculate the shear strength, not the shear modulus, but the shear strength, by using the 3-point bending test and keeping my sample size very small. So with this, I will end this lecture for today and hope to see you next time. Thank you.